Hi, my name is Chase Covington. I'm from Francis Marion University, and I work with Dr. Jackson of Ohio Wesleyan. And I work with him on studying measures of ecological stability. All right. So ecological stability describes how an ecosystem behaves after a disturbance. And we have different ways of measuring that. We have empirical measures of stability. Those are measures of stability that are taken from actual data. And then we have theoretical measures of stability, which are taken from the community matrix, representing that system. Okay, so looking through for this study, we were looking at 3 different forms of coefficients of variation for empirical measures of stability, those being the average population CV, the weighted average population CV, and the community CV. And then for our theoretical measure of stability, we were looking at the volume of the covariance matrix due to species interaction, the asymptotic resilience, which describes the long-term rate of return of the system after a disturbance, the initial resilience, which describes the short-term rate of return, and the intrinsic stochastic invariability, which describes the variation of the system whenever you disturb it with white noise. Okay, and for this study, we were using a MAR1 process defined by the population abundance vector at time t equaling a vector of constants plus the community matrix times the population vector of the previous time step plus some stochastic process error. Okay, so this study has 3 focuses. Number 1, we're trying to see, is this process that we're using a good process to use to estimate the B matrix, the community matrix? So to estimate the community matrix, we were using the conditional least squares method. And we wanted to see, 1, is this a good estimate? Is it accurate? And 2, does it provide an accurate estimation within a realistic amount of time? 1 time step equals about 1 week, so we can't go for too long, like 100 weeks. So after running a simulation with many different time steps, I found that 30 time steps seemed to be the lowest amount of time steps that provided a sufficiently accurate estimate of the community matrix. For any future time series simulations, I use 50 time steps though, because that is still realistic and more accurate than 30 time steps. Our second focus for this study was trying to see if there's any correlation between empirical measures of stability and theoretical measures of stability. So looking at these graphs right here, we do not see too much correlation. Our highest R² value is 0.2. So we're not seeing pretty much any correlation between empirical and theoretical measures of stability. We might want to look later on as far as what that actually means, but that just might mean that they measure different things. So our third focus for this study is comparing 2 different theoretical measures of stability. So as you'll see right here, the blue dots represent the data of 10,000 systems, and the black curves represent curves that show the upper or lower bounds of our inequalities. And so comparing the theoretical measures of stability that I discussed earlier, we developed these 2 inequalities right here, that our initial resilience is less than or equal to the negative half log of 1 minus our stochastic invariability, which is less than or equal to our asymptotic resilience, which is less than or equal to the negative log of our volume of the covariance matrix due to species interaction. And we also found that the stochastic invariability is less than 1 minus the square of the volume of the covariance matrix due to species interaction. So our next step for this is to, number 1, provide a rigorous proof for these inequalities that we found. This is just what the data suggests. We don't have a proof for it yet. And then also something we want to look at is as we were increasing the number of species for these comparisons, this is with 3 species. As we increased the number of species, we saw that the data clouds condensed away from the curves representing the bounds of the inequality. The inequalities were still true, but that curve is not as evident from the data as you increase the number of species. So we would want to see, are we just not sampling the systems well enough, or are we, do these measures of stability start to measure something different as we increase the number of species? Thank you.